Hello, everyone. Thanks for joining this session and to discuss on quantum computing. So, I would be going in detail about quantum computing. Previously, we had overview of quantum computing, and, uh, and as part of this quantum computing, and utilizing quantum computing utilizes the principle of quantum mechanism. What is that quantum mechanism? Like superpositioning and entanglement, and to perform calculation offering potential for solving complex problems that are too difficult for classical computers. As part of this, what makes quantum computer different, right? There are classic computers, quantum computers. So, what is the difference? So, using use of bits, which are either 0 or 1. In case of quantum computers, using quantum bits which can be 0 or 1 or both at the same time. And we'll be going in detail about superpositioning in subsequent slides. And so typically, as part of classic computer, there are two things. One is classic computers, then quantum computer. Typically, whatever we have a laptop or typical computers of and then we have as part of quantum computer windshields shape, typically as part of classic computer it has one state at a time, whereas in quantum computers you have multi-state at a time. Then comes we'll be going detail about entanglement, superposition, interference, and quantum gates. And as part of this, bits are independent of each other, are 0 or 1. Then in case of quantum bits, uh, are the no, quantum bits are combined. Then, as part of the superpositioning, if we roll a coin, either it will be heads or tail, right? So, if we have the chance of getting heads and tail, if it is 50%, or chances of getting head 0 or 1, 85%, and then getting 1 at 15%. Similarly, the superpositioning for 0 and 1, where 0 is 15%, and as part of 1, 85%. Advantage of quantum computing in the massive parallelism. Due to superposition, quantum computers can process a vast number of possibilities simultaneously. Speed to specific problems, exponentially faster for certain algorithms. Example, factoring large number with source algorithm, or searching with Gover's algorithm. Efficient simulation of quantum system, natural fit for simulating molecules, atoms, and quantum systems. Very hard for the classical computers. Then comes, if you go in detail about applications of quantum computing, as part of cryptography, a breaking RSA encryption source algorithm which is being used, creating quantum safe encryption. That's the idea about cryptography. As part of drug discovery, simulating molecular interaction to find new drugs. Then comes material science, design new materials at the atomic level. Finance perspective, portfolio optimization, fraud detection, risk modeling. And logistics, routine optimization, supply chain and improvement, AI and machine learning. As part of this speeding up learning algorithm, quantum enhanced data analysis. Then comes climate modeling, simulating complex climate system with higher accuracy. As part of energy, battery design, nuclear fusion modeling, then energy grade optimization. Application of quantum computing. We'll go in detail about cryptography. Quantum computers can potentially break certain classical encryption algorithms, but they can also be used to create an unbreakable quantum encryption. As part of optimization, quantum computers can be used to optimize complex systems such as logistic and supply chain. Then comes simulation. Quantum computers can simulate complex quantum systems, which can lead to breakthrough in the field like chemistry and material science. Then comes as part of machine learning, quantum computers can be used to speed up certain machine learning algorithms, leading to faster and more accurate predictions. Solution. The firm uses D waves, quantum anni- annihilator, or the IBM Quizstate Quizstate on a quantum simulation to solve quadratic unconstrained binary optimization QO QO or problem equivalent of portfolio selection task. And as part of QO format, transactions translate the portfolio optimization model into QO format, map constraint and objectives into qubits. Example, minimize variance, stay with risk tolerance. Run quantum algorithm like quantum annealing to find optimal or near optimal combination, and compare result with classical solutions. If we compare the result with classical computing, typically as part of matrix, a computation time which classical computer takes is 10 hours plus, whereas approximately quantum computing takes 2 to 5 minutes. Then comes solution accuracy, good, comparable, or better. Flexibility of constraint limited in case of classical computing, and as part of quantum computing it's very high. Real time responsiveness low, and high in quantum computing. Then comes as part of the business impact, faster decision making in the firm rebalances its portfolio faster than the competitors. Better risk management, more adaptive risk modeling under a volatile market. Then operational efficiency respective, um, reduce reliance on heavy computing infrastructure. Additional applications in finance, the use cases are like mm, fraud detection, faster pattern recognition using quantum machine learning, derivative pricing, improved Monte Carlo simulation via quantum acceleration. As part of risk modeling, more accurate simulation of rare events, fail risk, then market simulation, simulate complex market interaction and sentiment dynamics. Why is quantum computing helpful? As part of this, the computational power solves problems in seconds that would take classical computers thousands of years, and scientific discovery helps understand and simulate nature better, especially useful in chemistry and physics. Then, as part of economic advancement, and early adapters can gain a significant edge in industries like pharma, finance, and energy. Entanglement, if you go in detail, what is it? If you have a coin and toss it, so either the output is 0 or 1, right? So, the probability distribution which is done, and that 25% 0 0 or 0 1 10%, the probability of 10 is 40%, and 25% for 1 1. So the distribution of the qubits or 7 qubits is 2 to the power of n, that is 128 distribution. Similarly, for two number of qubits, 2 it is 4 distribution, then 5 32. Interference perspective, so qubits, so a coin in which is tossed, whether it's 0 or 1, right? The visualization part, it might be inclined to 0 or 1, or the probability of 0 and output of 1 varies. Clearly, they're described by waves, right? Typically, and the quantum wave function. And in this visualization, if you see, if you have different waves, and if you uh, uh, distract interference, will come with this kind of waves, right? Typically output. So having said that, in summarizing quantum weights, quantum wave functions, no, if you add the waves and distract or um, the overall wave functions, then probability distribution, and wherever you find that the answer on measurement, get one answer out, right? So quantum gates are the building blocks of quantum circuits, and they are used to manipulate quantum bits to perform various operations. Here is an overview of some common quantum gates. So typically, we'll be going in detail about single quantum gates, then two qubit gates, and multi-qubit gates. As part of single qubit gates, the Pauli X gates, then Pauli Y gate, Pauli Z gate, and Hadamard gate, phase gate, and as part of two qubit gates, C naught gate, CX, then swap gate, CZ gate, multi-qubit gates, Toffoli gate, CC Knot, then Franken gate. As part of this quantum gate properties, unitary quantum gates are represented by unitary matrix, which preserves the norm of qubit gates. Reversibility perspective, quantum gates are reversible, meaning that input state can be recovered from the output gate. Then comes application of quantum gate algorithm. Quantum gates are used to implement quantum algorithms such as source algorithm and Gover's algorithm. Quantum error correction. Quantum gates are used to implement quantum error correction codes which protect quantum information from uh, decoherence. Quantum simulation. Quantum gates are used to simulate complex quantum system which can lead to breakthroughs in the field like chemistry and material science. Uh, at last, I would like to convey over here is that computing doesn't replace classical finance tools yet, but it enhances high complexity computations in ways classical systems can't match. Firms investing in this early are built future-ready infrastructure for finance. So basically, what I would like to convey over here is that uh, it's not computing things will be replaced, but it will be used as enhanced or improved in efficiency, improved in the speed aid of the competition. Thank you.